Hey everybody, I just wanted to go over this problem, review problem about acids and base titration, buffer, all that good stuff. Okay, and so let's get right into it. So here, if we look at part A, basically we have formic acid and we're just trying to find the pH of that. Keep in mind there are two types of equilibrium problems. There are equilibrium problems where you have to find the K, the equilibrium constant, or the conditions, which is the values at the equilibrium part of the reaction. So when we get started on this, what we're going to want to do is, for part A, we're always going to want to write a reaction. Keep in mind the reaction for the equilibrium acids are always, for the weak acids, are always the same, and the reaction for the equilibrium bases, for the weak bases, are always the same. And so this reaction is an acid, formic acid, so it's this plus water reacts to form the hydronium ion plus the formate ion. Okay. Now, in order to fill out our ICE chart, where'd that come from? Don't want to distract you with that. But in order to fill out the ICE chart, okay, let's do some of this here. ICE. We need to know what this is, and keep in mind that we need to know this in molarity, capital M molarity. So when we do that, we get, okay, from the problem, we get 4.60 grams of formic acid. Okay, so in order to go 4.60 grams, to convert it from grams to moles, we need the molar mass to put in here. So H in this case is, there's two of them, 1H, 1H, and they have a mass of 1. Okay, and then there's a C, there's one of them that has a mass of 12. There's an 8, there's an O, which then there's two of those, which has a mass of 16 each. So this is 2 plus 12 plus 32, and that equals 46. Now I don't need my calculator, so I can do that. And so now 4.6 grams times 1 mole per 46 grams. And so that equals, let me get a little bit of space here, that equals 0.1 moles. But we need to have the molarity, so 0.1 moles divided by how many liters? 1 liter. See, it says right here in the problem, 1 liter of solution. Okay, so divided by 1 liter. That equals 0.1 molar. So now we're going to go here, we're going to go 0.1. Now, this doesn't matter. We're going to do 0 here, 0 here. Okay, so now we're going to subtract x. Keep in mind that reactants are lost during a reaction, and the products are gained. So this is going to be minus x, so it's 0.1 minus x, x, and x. And what we're trying to find in this is this value right there, because from there we can calculate the pH. Okay, so to do that now, we need to use the Ka. Ka equals 1.7 times 10 to the minus 4. Where did you get that, Walsh? Well, I read the problem and it's right there. Okay, and so, and that equals products, which is x over 0.1 minus x. Okay, so what we're going to do is we're going to use the 5% rule. By doing the 5% rule, we can get rid of that. And now we can solve this for x. So we multiply both sides by 0.1. So let me turn on my calculator. So we get 1.7 times 10 to the minus 4 times 0.1. And we get 1.7 times 10 to the minus 5, and that equals x squared. And so now we do the square root of that, and that's, so x is going to equal 0.00412. It can also equal 4.12 times 10 to the minus 3. Okay, now that's not done because the question asks for the pH. The pH of the solution now is taking the negative log of this value in blue. So now we're going to do pH equals the negative log of the concentration of the hydronium ion. And the concentration of the hydronium ion is that value right there, right? Okay, 0.00412. And so I'm going to put that in the calculator, negative log of that answer. And so we get a pH equal to somewhere around 2.38. Okay? Now, let's look at part B. Part B says now what you're going to do is you're going to mix 100 milliliters of HCl. Okay? Now, once we mix the 100 milliliters of HCl, we want to know what's going to happen to the formic acid. Okay? So now, is this a buffer titration problem? Well, not really, because what we're doing is we're doing a mixture of a weak acid and a strong acid. Okay? So if it's a mixture of a weak acid and a strong acid, okay, we pick the acid with the higher pKa, or Ka, which happens to be the strong acid, which happens to be HCl, and that dominates the solution. And then we find what the concentration of HCl is. Okay? And so it's 0.1 molar HCl. Okay? 0.1 molar HCl. So the pH of that solution is really just going to be the negative log of the concentration of the hydronium ion. And for strong acids, the concentration of the hydronium ion is equal to the concentration of the acid. So we're going to do pH equals the negative log of 0.1, and the negative log of 0.1. Wow. Okay, let's move this so that you can see what let's see. There, how's that? Negative log of 0.1 is equal to 1. Okay. And any of the concentration from the formic acid is going to be negligible. Okay. So now for part C, it says a new solution of formic acid and sodium formate there. So now that we have formic acid and sodium formate, now that is going to give us a buffer solution. It's a weak component, in this case it's a weak acid, mixed with the salt of the weak acid. Okay, that's a buffer. So C, if we know that that's going to be a buffer problem, and we're not adding anything to the buffer, we're just mixing the buffer, okay, then we know that we need to do just an equilibrium problem. So again, we're going to do HCHO2 plus H2O is in equilibrium with H3O plus CHO2 minus. Now, let me just make sure we have the concentrations correct. So it says, so it's 1 liter of solution, so it's 0.15 moles of sodium formate, the formate ion, and 0.1 moles of this. So this guy, here, let me change colors just to make it a little easier. This guy is 0.15 moles per 1 liter, and so this concentration here is going to be 0.15. And then this concentration is 0.1 moles over 1 liter, which is 0.1. Now, there's our ICE. Okay, and so now we go through this, we do this, and this, and this, and then this. Okay, so now this is what we want to start with. This doesn't matter, sorry, not start with, but this is what we want to see. That's 0, so we're going to do minus x plus x plus x, 0.1 minus x, x 0.15 plus x. Okay, this 2 is not squared, that's part of the problem up there. And so now 1.7 times 10 to the minus 4, the equilibrium constant, equals products x times 0.15 plus x all over the reactants, which in this case is 0.1 minus x. Okay, so now we use the 5% rule, and these get rid of, and so now we solve this for x. So we take 1.7 times 10 to the minus 4, so we're going to multiply by 0.1, and then we're going to take that and we're going to divide it by 0.15, and that equals, so we get x equal to 1.13 times 10 to the minus 4. And that is equal to the concentration of the hydronium ion. But I think the question asks for the pH. So the pH, then, we have to take the negative log of this solution. So the negative log, so pH equals negative log of H3O plus. And so that equals, so then we do negative log of second answer of that guy, and we get 3.94. Oh, we have to round up, so 3.95. Okay, great. So that's our pH for part C. Now for part D, says we're going to take this mixture and we're going to bubble HCl through it. Okay, so this is part of our titration. Okay, we're going to take a buffer and we're going to add an acid to it. Okay, so for part D, this is where it gets really fun, because we're going to take 0.000, how many zeros? Just make sure. I'm sorry that I keep going up and down here. 2 zeros, 5. Okay, so 0.005 moles of this solution, and we're going to bubble it through. Now, HCl. So when we're doing this, when we're adding stuff to a solution, we can consider that a titration. Okay, and when that happens, we have to do a stoichiometry ICE chart first, and then an equilibrium ICE chart. Okay, so with the stoichiometry ICE chart, the whole point of the buffer is to react away the strong acid, which is the thing that is going to affect the pH the most. So we want to react the strong acid away, and so we get an acid plus a base. So now what's the base? Well, the only other things in the solution are HCHO2 and CHO2 minus. This is the acid, and this is its conjugate base. So the base that we're worried about is this one, is going to form CHO2 minus. And now we do our proton transfer, equals HCHO2 plus Cl minus. And so now we can do an amounts table, or an ICE chart, what I call a stoichiometry ICE chart. And when we do our stoichiometry ICE chart, let's see, I think that this was 0.005 moles. Okay, remember, we're doing this in moles. Stoichiometry is in moles, so it's 0.05 moles. And for this, it's 0.1 moles of formic acid and 0.15, because it's asking for the part C. So this is 0.15 and then 0.10. And we don't care about the chloride. The chloride's a spectator ion. So now, what is our limiting reactant? This guy. Okay, it's present in the least amount stoichiometrically. So we're going to subtract to get this down to 0.005 minus 0.005. Now this is a product, so it's plus 0.005. And now when we do this math, we get this 0.145. Let me put my leading zeros in there, 0.105. Okay, and now that's how many moles there are. Okay, so now the whole point of the buffer is that now all the strong acid has now gone. We've reacted it away, and so we want to use that. Now we can figure out what's left, which is a weak acid and its conjugate. And weak acid and conjugate means that we have an acid, or we have a weak acid equilibrium problem, or a weak acid buffer equilibrium problem. So we're going to write, this is what I always say, keep the reaction the same. So even though that this is a reactant in this case, we want to keep the reactants the same when we write our weak acid equilibrium. So we have HCHO2 plus H2O is in equilibrium with H3O plus CH2O2 minus. Okay, and now this is all. So now this is our equilibrium ICE chart, and this is done in capital M molarity. Okay, well, how many moles do we have of HCHO2? Well, it's moles divided by 1 liter. Let's just make sure that that's right. Okay. So bubbled through 1 liter of solution. So the concentration here of formic acid, this one, is 0.105 molar. We don't care about water. This is going to be 0. And now this is going to be, divided by 1 liter, is going to be 0.145 molar. Okay? And now we do our equilibrium ICE chart. Minus x plus x plus x. So it's 0.105 minus x, x 0.145 plus x. And now we solve. Okay, A equals 1.7 times 10 to the minus 4 equals products x 0.145 plus x all over the reactants, which in this case is just 0.105 minus x. We're going to use our 5% rule, and so that gets rid of this and this. Okay, and so now we can solve this part of the problem. Okay, so we go 1.7 times 10 to the minus 4th times 0.105, and then we divide it by 0.145. And so we get x equal to 1.23 times 10 to the minus 4 molarity. And that happens to be the concentration of H3O+. Now what we need to do is we have to convert this to pH. Okay, so the pH equals the negative log of the concentration of H3O+. And now we go negative log of 1.23 times 10 to the minus 4. And so we do negative log of that guy. And so the pH now, even though we've added all that HCl, the pH of this solution is 3.91. From part C, the solution was 3.95. So the pH hasn't changed much. The change, and this is extra, the change in pH is only about 0.04 pH units, which is exactly what a buffer does. Okay, that's what a buffer does, is to limit the change in the pH. Okay, so I hope that helps, and have a great night.